Okay, in this section of notes, we're going to be talking more about how atoms combine and join together and kind of what they form and how they form them. Um, just kind of a quick tour of the whole process, since we aren't really focused on the chemistry of it. We're kind of focused on how this relates to minerals and how minerals form and all that. So some forces, kind of a brief overview of it. Some forces within an atom. This first one, the electromagnetic force, that's just when opposites attract. And I'm guessing that most of you have, at some point played with magnets and, that positive end and the negative end will be attracted to one another, whereas two positives repel each other, two negatives repel each other. So that electromagnetic force, that positive being attracted to the negative charge, that's the attraction between the protons, which have a positive charge, and the electrons, which have a negative charge. So that's one of the forces, the first one. The second one, the strong force, when that's just what we call it, it basically holds the nucleus together, which it kind of has to be a strong force because protons are positive, so it's holding, depending on the atom, multiple positive charged bodies, up against each other, when that's not really something that they want to do. So like I said, that kind of holds the nucleus together. The protons and then the neutrons as well kind of get held together with strong force. The next one, weak force is responsible for atomic decay and radiation, which can also, under the right circumstances, lead to the decay of other atoms. We won't talk a lot about it, but it is one of the kind of the four main forces. And then gravity. Gravity is the weakest of all four, and compared to all of them, it is fairly weak, even though to us, gravity seems to be a very strong force. That's because gravity depends on, or the strength of gravity depends on two factors. The first factor is the size of the objects. And the second is distance between the two objects. So for us on Earth, the Earth is huge compared to us, so it's going to have a lot of gravity, and we are really close to the Earth, about as close as you can be. So to us, the Earth's gravitational force is very strong, but compared to other forces that are out in the universe, it's not as strong as some of the other ones. All right, so now we'll kind of get into talking about combining atoms and different elements and what you get. So compounds are something that you get when elements are combined chemically. And the chemically part, that's the most important part of the compound, is that those elements are joined chemically. So they're joined at an atomic level. It's not just some stuff thrown together. These are things that are reacting with one another and combining at the atomic level. When that happens, when these different elements combine chemically, they form molecules, which is just kind of a single grouping of the elements that make up a compound. And these are some different ones, just some examples. And here we have a carbon, two oxygens, and that's carbon dioxide, two hydrogens and an oxygen, so H2O, water. This one's methane, which is natural gas, CH4, NH3, this one's ammonia. I don't know what this one is. Something with boron and fluorine. To which one? Let me go back to this one.
More.
One more?
Yeah.
That one?
All right. Yeah, you good.
Okay. So some different molecules, different compounds, and all of that. So moving on. Some properties of compounds. Compounds are pretty cool stuff. There are a lot of them. The first one is that you end up with a new substance, something that's different from the other ingredients, the other elements that go into the compound. It's something new and it's something different. And with this example, we'll use salt. So as the formula NaCl is sodium chloride. You just have some sodium, you have some chlorine. Sodium by itself, pure sodium, it's a metal, it's a soft metal. You can cut it with a butter knife. It kind of has a consistency of, I don't know, maybe like cheese, like a stiffer cheese, maybe not like a Parmesan, but maybe a nice sharp cheddar, maybe. But if it's exposed to air and moisture in the air, or if you put it into water, it will explode and burst into flames, and it's dangerous stuff. So much, that when you store sodium metal, you store it in a jar with oil. So the oil keeps air from getting to it, and it keeps water from getting to it, so it doesn't explode somewhere in a closet. Chlorine gas, elemental chlorine gas, is extremely poisonous. It's even been used as a chemical weapon in World War I, and some other places. And what happens there is essentially the chlorine gas, if you breathe it in, it reacts with the moisture in your lungs and turns into hydrochloric acid, which is not something that you want inside your lungs. But you take those two things, something that's a metal that, is very volatile and, potentially explosive, chlorine gas, which is deadly, and it makes table salt, something completely different from both of them. And in all actuality, table salt is something that your body has to have. You have to have salt. If you somehow manage to, not have salt in your diet, if it were a long enough period of time, it would kill you. You have to have salt. And I'm not saying or condoning, going out and eating a bunch of salt. That's not good either, but you have to have some. But the big thing is it's completely different from the other two things that make up the salt. Compounds also have formulas. So, with salt, it's sodium chloride, NaCl. If it's, different from that, then it's not salt. There are other types of salts, but, it's not table salt. And since compounds are joined together chemically, if you're going to separate them, you have to separate them chemically, which is a much more difficult undertaking. It's often a lot more dangerous. It's a lot more involved. Something like salt, to separate salt back into sodium and chlorine, you need to melt the salt, and then you need to run an electric current through it. And then when you do separate them, then you end up with this metal that's reactive to air and moisture and poisonous gas. So it's dangerous. It's doable, but it's dangerous in a safe lab setting. But that's because, again, they're combined at the atomic level. So different ways that these atoms can kind of combine and join with other atoms. The first one is an ionic bond. So in an ionic bond, electrons are transferred, they're given to other atoms. When this happens, that forms an ion, which is just an atom with a charge. Normally, an atom has no charge, because if you remember back to Wednesday, the atomic number tells us how many protons there are in the nucleus, and that equals the number of electrons. So the positive protons and the negative electrons, they cancel each other out as far as charge goes. So a normal atom has no charge. But in this example, we have two atoms that each have one electron. Since this is the first energy shell, they both want two in that first energy shell. So this atom gives an electron to this other atom, which causes or creates an ion. If an electron is given, if some negative energy is given, then that atom is going to be positive because it got rid of some negative charge. If an atom receives an extra electron, then it's going to have a negative charge because it's received an extra electron. So if if an atom is giving away an electron, it's going to have a positive charge. If it's receiving an electron, it's going to have a negative charge. Typically, these ionic bonds form crystals. This is another example of salt. So you have your metal, which is the sodium, and non-metal, which is the chlorine. They form this nice cubic crystal structure. And something, as we talk more about minerals, we'll talk about crystal structure. And the thing that determines what shape the crystal is how the atoms are arranged inside that. And like I said, these arrange themselves, really nice and neat into, kind of cubic shape or box or rectangular shape. Right, the second type of bond is a covalent bond. And the big thing about covalent bonds is that atoms share electrons. So again, we have two atoms with one electron each. So they end up sharing an electron. So they effectively have two electrons each, which is what they want in that shell. That kind of makes them happy. Covalent comes from whatever the outer shell is, the outer energy shell is for an atom. That's called the valence shell. Those are the valence electrons. So co as a prefix, just like with cooperate, cohabitate, things like that, where you're working with, coordinate, working with somebody else, kind of joined and working towards a common goal type thing. That's what these electrons are doing. The valence electrons are kind of working together. So, all right. A lot of times covalent bonds will form with gases. So, these gases, hydrogen, oxygen, nitrogen, chlorine, you're not going to find one oxygen atom just floating around in the air. It's not going to happen. Oxygen's way too reactive, so it's either going to find another oxygen to form a bond with, and then O2 is going to float around and we can breathe that, or it's going to react with something else. But you're not going to find these gases just one single atom just floating around. It's just kind of not, they're just too reactive. And so we've talked about compounds and how those are joined together chemically. This last little section is about mixtures. So this is when elements or in compounds are joined physically, or I guess combined physically. So this is not at the atomic level. This is much, it's much easier to separate these than it is with a compound. In the picture, if you have a pile of M&Ms, that's really easy to separate those. Red pile here, blue pile here, brown pile here, yellow, orange. You can put them in piles. It's super simple. With the sand, get yourself a pair of tweezers and a magnifying glass and knock yourself out. Have a great weekend with it. You could do it. Not that anybody would really want to, but it's possible. Or with the orange juice, if you needed to separate that, if you needed to extract the water from that, you could, and then you would have, orange juice concentrate left in the glass or whatever, and then you can get that water back out of it. So much simpler to separate mixtures versus compounds. So one property of a mixture is you don't get anything
Go
new.
back.
What's that?
Sorry, could you go back?
Yeah. To that one?
Yeah, and one more. Okay, thank you.
With a mixture,
Strong.
what?
This nigga just, bro, chill, get out. All right, so will you upload this class onto Canvas
I'm going to
or like the recorded class? I mean,
what?
like, cause this class is recorded, right? This is being recorded, right?
Mm-hmm.
Yeah, like, will this be on Canvas?
There will be a link to my YouTube page.
Okay, thank you.
You're welcome. So with mixtures, with a compound, you get something new that's different. With a mixture, you don't get anything new. With this example, you mix salt and water together, you get salt water. But again, it's going to be really easy to separate those two things. If you're trying to get the salt back out of it, if you have time, just set the glass out, let the water evaporate, and the salt's left behind. If you need to speed it up a little bit, heat it up, and that'll kind of pick up the pace on that. But it's a lot easier to do that with a mixture versus a compound. Mixtures also don't have a formula. These are both pizza, I guess. One for sure, the other, technically I guess it's pizza, but it's clearly not the same formula, but they're both still pizza. And there might be, ratios or kind of a recipe, so to speak, that you could, follow or whatever to make a mixture, but it's not a formula. It's not like there's only one way to do it and that's it. And then the last little one, which we've kind of touched on before, you separate them physically because they're combined physically. It's not at the atomic level. It's just a physical combination where you can just separate them much more easily. Are there any slides that I need to go back to?